Hello, and thank you for coming. This is the Project 2 poster by Team 71 for their model of a smog-free tower. At the start of the project, Team 71 created a set of goals that they hoped to accomplish by the end of the project. The first goal was to create a basic model of the smog-free tower. The next goal was to develop a list of alternative prototypes for each aspect of this basic model. The third goal was to create a mathematical model to determine effectiveness of each of these alternatives for the smog-free tower. The fourth goal of the team was to select the best alternative out of the ones that they had laid out. And finally, the team hoped to understand the effectiveness of the tower at a larger scale and create a plan for its implementation if it was deemed effective. The first thing the team laid out was some design specifications for what they wanted to see from the total model and also from each of the parts of the prototype. For the total model, some important things to consider were to account for as many variables as possible, to account for energy needed, and to determine the effective range given both of these things. For the alternative prototypes, some of these design specifications included the fan's energy usage in regards to its airflow and radius, and the pre-filter's effectiveness and its subsequent airflow cost. The final thing the team did before beginning to design their models was to create a basic current model that they could use to select alternatives and develop prototypes. The first part of this base model was a fan, which ensured that air would flow through this tower at a greater rate than it would if it was simply sitting there. Additionally, the team implemented a form of electrostatic attraction, seen here in yellow, that would increase the rate that these small particles were attracted towards the tower. The next and most important part of this was the electrostatic filter, which included the use of a grounded plate and some other plates set up to ensure that all these small particles would get caught. Additionally, it's important that there is a structure outside of these electronic filters and possibly a pre-filter included on this structure. Finally, it was important to come up with a method for cleaning this smog-free tower, as this small particles would build up over time, and the team decided that a fire hydrant could be used for this.
In order to model the system, some assumptions and simplifications were made. Smog particles were simplified to having the density of air, the equivalent charge of an electron, and a diameter of 2.5 micrometers. These three assumptions about smog essentially follow a less than ideal scenario, where the smaller charge will limit the effectiveness of the electrostatic force, and the larger diameter will increase the mass of the particle and decrease the effectiveness of all forces. The components of the system to be modeled would follow three significant parts: parallel charged plates, charged electrodes, and a fan. The model was simplified to separate behavior outside of the tower and inside the tower. Outside the tower, the horizontal drag force due to the fan would be taken into account. This fan would create a fluid velocity for air particles equivalent to the volumetric flow rating of the fan, divided by the current area of the circle made by the current radius the particle is from the fan. As such, this drag force decreases as the distance from the tower increases, which gives the tower a limiting range. Inside the tower, the downward electrostatic force from the charged plates would be taken into account, where the electric field due to the plates would follow the potential difference between the plates divided by the distance between them. Along with this, a constant horizontal velocity is assumed inside the tower, where the volumetric flow rating of the fan causes a fluid velocity which the smog particle is now caught up with. Both inside and outside the tower, multiple forces are ignored for simplicity. The buoyant and gravitational forces have been omitted from the model, since the densities of air and smog are roughly the same, with negligible effects from the specific type of smog and changes in temperature. This omission also is on the grounds of the fact that since the smog is around the effective region of the tower, neither the gravitational nor the buoyant force has been overly influential. The electrostatic force due to the electrodes has also been omitted. This follows the simple logic that the smog particles will only obtain a significant amount of charge after they have been induced by the electrodes. As such, the electrodes themselves will not have a negligible effect on attracting the smog particles towards the tower. Along with the assumptions around the forces involved, the model must also make some assumptions with respect to energy usage. The energy used by the fan would follow a proportion where, for example, at half the volumetric flow rating for a given fan model, half of the energy would be used. The energy used by the charged plates would follow the power required to flow 1 ampere through the system for a given potential difference between the plates. And finally, the energy used by the electrodes would follow the energy required to isolate the point charges of the electrodes given the distance between the electrodes.
Two separate MATLAB codes were utilized to implement the fluid dynamics described by Zach into a user-friendly model. One of the codes models the airflow of particulate outside the tower and outputs a graph of particle distance from the tower over time for particulates starting at different distances from the tower, as seen here in this graph. This graph reveals the effective range of the tower for the given specifications. This is implemented through the use of a while loop, incrementing time and recalculating the distance from the tower based on the particle's original position. As this while loop runs, the x and y values are calculated and compiled into a list that is graphed upon either the distance from the tower reaching 0 or a preset maximum runtime being reached. The second MATLAB code models the particle motion within the electrostatic precipitation chamber of the smog reduction tower. This code outputs a graph of the vertical and horizontal distances from the charged plates of the particle. This graph reveals the maximum starting height for a particle to be trapped by the device, as the plates are a length of 1 meter and any particulate that reaches a vertical distance of 0 and a horizontal distance longer than 1 meter will not be captured. This is implemented in a similar fashion to the other function, with a large while loop recalculating the horizontal and vertical distances of the particles and compiling them into lists that are later graphed when either the vertical height is 0 or a certain amount of time passes. To optimize the model, we configured it to consume 2,000 watts of power. For each additional level of plates added, the chance that a particle is too far above the plate on every single plate is reduced, but the voltage on each plate is also reduced. The team discovered that the optimal number of levels to have was 3, which resulted in virtually 100% of the particles being captured with minimal reduction to plate voltage. When the equations were plugged into the MATLAB model, some interesting issues were first discovered. The option for a pre-filter would not be feasible, as the fans used were too large, as they did not move enough air to cause the air to move at a velocity greater than the expected reduction in airspeed through the filter. Thus, this element was eliminated from our model. Once this correction was made, the model runs accurately and depicts the effects that an electrostatic precipitation-based smog reduction facility would have on the pollution particulate in the air surrounding it.
So, moving on to the analysis and conclusion, um, taking a look at the results of our model, essentially the team decided that these are kind of the specifications that should be used. So each tower would utilize 2,000 watts. The original tower had 1,700 watts each. So the tower's 7 meters tall, so the top 6 meters should include 60 electrode wires covering each of the 4 sides. The bottom meter will be reserved for the fan and power supply. So the fan should be 2,500 feet cubed per minute, and its range should be at least 8 feet. And this will take 500 watts of power. Now the electrodes should receive 5% of the power left after allocating to the fan. So the reason for the 5% power is because a charge of 10 to the negative 6 is already 10 raised to the 13th power times the expected smog particle charge. So 5% power should be enough to induce a proper charge on the particle. So next, the charge plate should receive 95% of the power left. This will be about 1,425 watts. So to power all of this, you need at least six 400 watt, 20 square feet solar panels. So the tower has an effective range of about 23 square meters. The tower itself only needs a 4 square meter base, so it can be placed in many areas. It doesn't require much space. So overall, the kind of conclusion that the team decided was if we stray a bit from the original design and try to maximize the efficiency of the tower, given with the numbers that we provided, it can lead to a higher effective range, and this will be lead to a greater proportion of particles captured by the system and fewer overall towers needed. But this would have a downside of a much greater power consumption, um, much more large industrial grade parts that will be needed, um, and also an increase in fan noise during operation, which, when placed in a bunch of urban environments with a high density population, may be a problem. So the overall conclusion is that the current design is an elegant and non-intrusive solution to the smog problem in urban areas like Hong Kong, uh, which the team has modeled to have a real expected effect on smog concentration. However, the design can be modified depending on the needs of the city and what they decide.